So we were discussing the Rutherford scattering. We have divided the Rutherford scattering into three parts. One is the calculation of the fraction of projectiles scattered at angles greater than some value of theta. Second one is the Rutherford scattering formula and its experimental verification. And the third one is the closest approach of the projectile into the nucleus. So we have already discussed this first two parts, and now we discuss the third one, the closest approach of a projectile to the nucleus. We know that the nucleus is positively charged and the projectile is also positively charged. So there is a repulsive force between the projectile and the nucleus. So the positive charge projectile slows down, or its kinetic energy decreases as it approaches the nucleus. So this is because a part of its initial kinetic energy is converted into the electrostatic potential energy due to the nuclear repulsion. So, whenever the projectile goes closer to the nucleus, it gains more potential energy and its kinetic energy decreases. So, we know that the potential energy U is equal to 1 over 4 pi epsilon 0 Q1 Q2 divided by R. So, here Q1 is the charge of the projectile, which is small z, and Q2 is the charge of the nucleus, that is capital Z. So Q1 into Q2 is capital Z small z E square divided by 4 pi epsilon 0 R. So from this we can see that as the distance between the projectile and the nucleus decreases, then 1 over R increases. So for the potential energy increases. The large distance from the nucleus, R is large and 1 over R is small, and therefore the potential energy is small. And the maximum potential energy occurs at the minimum value of R. So at this point, the kinetic energy is minimum. So for the shortest distance between the projectile and the nucleus, R is minimum. At this point, the potential energy is maximum and the corresponding kinetic energy is minimum. And far away from the nucleus, at a very large distance from the nucleus, R is very large, approximated to infinity. So the potential energy is 0. So at a very large distance from the nucleus, the projectile's potential energy is 0, and its kinetic energy is equal to its total energy. So this total energy equals to its kinetic energy because U is 0, and this is equal to half mv square. So now as the projectile approaches the nucleus, the kinetic energy decreases and the potential energy increases. But the total energy, which is equal to E equal to U plus K, remains constant according to the law of conservation of energy. So as this approaches, Ke decreases from the maximum value and U increases from 0. So at a particular point, U is maximum and kinetic energy as minimum. So that distance is called the R minimum. So the minimum distance, we can call it as R minimum. That means the minimum distance between the nucleus and projectile, R minimum. And at this point, the kinetic energy decreases, and therefore the velocity of the projectile also decreases, and the corresponding velocity is also minimum at this position. So we call this as V minimum. So at this point, at a distance R minimum, we can write the energy E equal to this kinetic energy, which is minimum, and the potential energy, which is maximum. So kinetic energy minimum is half m into V minimum square. And the potential energy maximum is 1 over 4 pi epsilon 0 Q1 Q2, that is small z capital Z E square divided by R minimum. Okay, so this is at the minimum distance between the nucleus and projectile. But we know that according to the law of conservation of energy, the total energy remains a constant. So at this point, far away from the nucleus, this energy is this, and near to the nucleus, the energy is this. So according to law of conservation of energy, those two equations should be equal. The energy at a farthest distance from the nucleus should be equal to the energy when the projectile is closer to the nucleus. So we can write this E. So this is when this projectile is away from the nucleus is equal to the energy when the projectile is closer to the nucleus. So therefore we can write half mv square is equal to half mv square minimum plus 1 over 4 pi epsilon 0 small z capital Z E square divided by R minimum. So away from the nucleus, the potential energy is 0, kinetic energy is half mv square, and the total energy is again U plus K, which is half mv square. And closer to the nucleus, the kinetic energy is minimum and the potential energy is maximum, and the total energy is the sum of those two. Okay, so this so we assume that this occurs at an impact parameter B. Okay, so angular momentum is also conserved in this case. So away from the nucleus, the angular momentum L, which is R cross P, that is equal to R cross NB. So here this perpendicular distance is B. So therefore P and this R are perpendicular. So MVR sin theta, that is MVR. So here R is 1. So the angular momentum here is MVB. But at the minimum distance, the angular momentum is, at this point the velocity is V minimum. So at this point the velocity is V. So at this point the angular momentum is equal to M into V minimum into R minimum. Okay. So according to the law of conservation of angular momentum when the projectile is far away from the nucleus, that is MVB. So angular momentum is actually R cross P. So R cross MV. So when they are when P and R are perpendicular, its magnitude is M into V into R. So when the projectile is at a distance equal to the impact parameter B, so then R equal to B, so that is MVB is equal to, when the nucleus is closer, the corresponding velocity is V minimum and the corresponding distance is R minimum. So MVB is V minimum, R minimum, M can be cancelled, and therefore we can calculate V minimum from here. V minimum is equal to V into B divided by R minimum. And now we can substitute the value of V minimum in this equation, and therefore we get half mv square is equal to half m into V minimum can be written as VB by R minimum. So V minimum square is V square by R minimum square plus 1 over 4 pi epsilon 0 small z capital Z E square by R minimum. So solving this equation, we can find out the value of R minimum for a different impact parameter B. So as the impact parameter B changes, the R minimum value also changes. From this equation, we can see that the kinetic energy of the projectile at R minimum. So that is this term. So this is the kinetic energy of the projectile at R minimum, and this is the potential energy at that point. So this is the kinetic energy at a far away point. So this is the kinetic energy at R minimum is not zero when B not equal to 0. So അപ്പോൾ ഒരു നോൺ സീറോ ഇമ്പാക്റ്റ് പാരാമീറ്റർ ആണെങ്കിൽ കൈനറ്റിക് എനർജി ഈ ക്ലോസസ്റ്റ് ഡിസ്റ്റൻസിലും ആർ മിനിമം വാല്യൂയിലും സീറോ ആവുന്നില്ല. കൈനറ്റിക് എനർജി മിനിമം ആവുന്നേ ഉള്ളൂ, അത് സീറോ ആവുന്നില്ല. ഓക്കെ, പക്ഷെ ബി സീറോ ആണെങ്കിൽ ഇമ്പാക്റ്റ് പാരാമീറ്റർ സീറോ എന്ന് പറഞ്ഞാൽ ഹെഡ് ഓൺ കൊളീഷൻ ആണ്. ന്യൂക്ലിയസിൽ നേരെ കൊളൈഡ് ചെയ്യാൻ ബി സീറോ ആണ്. ഇപ്പോൾ ഒരു പെർട്ടിക്കുലർ ഡിസ്റ്റൻസിൽ കൊളൈഡ് ചെയ്യുമ്പോഴാണ് ഇവിടെ ഒരു ഇമ്പാക്റ്റ് പാരാമീറ്റർ വരുന്നത്. ഇമ്പാക്റ്റ് പാരാമീറ്റർ ബി സീറോ ആകുമ്പോൾ നമുക്ക് പറയാൻ പറ്റും കൈനറ്റിക് എനർജി എന്ന് പറയുന്നത് ഹാഫ് എം ഇൻറ്റു വി സ്ക്വയർ ഡി സ്ക്വയർ ബൈ ആർ. കൈനറ്റിക് എനർജി സീറോ ആവുന്നു. ഓക്കെ, സോ that means the projectile would lose all its kinetic energy, and all the kinetic energy is converted into the potential energy. So that means in this case the projectile will approach closer to the nucleus. അപ്പോൾ ഹെഡ് ഓൺ കൊളീഷൻ ആവുമ്പോൾ, അതായത് ഇമ്പാക്റ്റ് പാരാമീറ്റർ സീറോ ആവുമ്പോഴാണ് ന്യൂക്ലിയസിനോട് ഏറ്റവും ക്ലോസർ ആവാൻ ഈ പ്രൊജക്റ്റൈലിന് പറ്റുക. വേറൊരു ഡിസ്റ്റൻസിലാണ് കുറച്ചുകൂടെ അപ്പുറത്തുനിന്ന് അത് സ്കാറ്റർ ചെയ്ത് പോകും. ആർ മിനിമം ഡിസ്റ്റൻസ് മിനിമം ആവുന്നത് വെൻ ദി ഇമ്പാക്റ്റ് പാരാമീറ്റർ ഇസ് സീറോ. സോ അറ്റ് ദിസ് പോയിന്റ് the distance from the nucleus is d. ആ ഡിസ്റ്റൻസിന് നമ്മൾ the distance of closest approach എന്ന് വിളിക്കുന്നു. And we can find this distance of closest approach by putting b equal to 0 in this expression. Okay, so when b equal to 0 here, the r minimum is equal to the distance of closest approach d. So therefore we get, so that is d. So this half mv square is also called the kinetic energy k. So d here is equal to 1 over 4 pi epsilon 0 z square by k, where k equal to half mv square. So this is the expression for the distance of closest approach. So the distance of closest approach is there when the projectile approaches head on, that is when the impact parameter is 0. So these are the kinetic energy, potential energy and angular momentum of the projectile when the projectile is far away from the nucleus at an impact parameter b. So these are the potential energy, kinetic energy and the angular momentum of the projectile when the projectile is closer to the nucleus at a distance r minimum. And this occurs at an impact parameter b. So when the impact parameter b is equal to 0, or when the projectile is fired for head-on collision towards the nucleus, then the r minimum is equal to d. So this is the smallest distance between the nucleus and the projectile, and it is called the distance of closest approach. And at this point the kinetic energy is 0 and the potential energy is maximum, z square by 4 pi epsilon 0 into 1 over d. Okay, and this u is equal to the kinetic energy when the projectile is far away from the nucleus. So this is the total energy here. So this should be equal to the total energy here. So this is equal to half mv square, and from that we can find the value of d, that is z square by 4 pi epsilon 0 into 1 over kinetic energy. Okay, so here the alpha particle or the projectile is directed straight towards the nucleus with an initial kinetic energy k. So as the projectile approaches the nucleus, its kinetic energy decreases and the potential energy increases. So at the distance equal to the distance of closest approach, kinetic energy becomes 0 and the particle stops and it cannot go closer to the nucleus. So it retraces its path by turning through 180 degrees. So there is a back scattering. It completely scattered back. So at this distance of closest approach, the entire initial kinetic energy of the projectile is converted into the electrical potential energy. So half mv square is equal to the potential energy here, and from that we can find out the distance of closest approach. Okay, so but when impact parameter is non-zero, the R minimum value is not minimum, is greater than D. അപ്പോൾ അവിടെയും ഒരു ഡിസ്റ്റൻസ് ഉണ്ട്, മിനിമം ഡിസ്റ്റൻസ് ബിറ്റ്വീൻ ദിസ് projectile and the nucleus, but it will be greater than the D. D എന്ന് പറയുന്നത് minimum distance, and that is possible when the nucleus, when the projectile approaches the nucleus in a head-on collision. That means the impact parameter is 0. So as the impact parameter increases, the distance of the minimum distance between the projectile and the nucleus also increases, and we can see that the angle of scattering decreases. ഇതിൽ 180 ഡിഗ്രി ആയിരിക്കും. ഇനി ഡിസ്റ്റൻസ് നമ്മൾ കുറച്ചുകൂടെ ഇൻക്രീസ് ചെയ്യുകയാണെങ്കിൽ then this angle of scattering decreases. ഇതിൽ ഈ ഹെഡ് ഓൺ കൊളീഷൻ ആകുമ്പോൾ 180 ഡിഗ്രി ആയിരുന്നു, ഇവിടെ greater than 90 ആണ്. Again നമ്മൾ impact parameter increase ചെയ്യുകയാണെങ്കിൽ then the projectile is scattered through an angle less than 90. So the projectile tending to collide head-on with the nucleus slows down due to the repulsive force of the nucleus, and it finally stops and it is repelled back. So this projectile retraces its path scattered to an angle 180 degree. So this kind of alpha particles or projectiles with an intermediate impact parameter. So for head-on collision, the impact parameter is 0, and for intermediate impact parameter, so they tend to hit the nucleus, but with a lesser there will be a small repulsive force compared to this, and they are scattered through large angles greater than 90 degree. So those kind of alpha particles with large value of impact parameter will experience a small repulsive force from the nucleus, and they are scattered through small angles. So this alpha particles with a larger B will pass through larger distances without any deviation. Without deviation അതിൽ pass ചെയ്യാനും പറ്റും. Okay. Now we can do a problem. Find the distance of closest approach of an 8 million electron volt alpha particle incident on a gold foil. So we know that the expression for the distance of closest approach is given by Ze square by 4 pi epsilon 0 1 over k. So here a simple formula is used where Z E square by 4 pi epsilon 0 is written in million electron volt femtometer. Okay, you can do this in another method also. You can convert this energy, kinetic energy, which is 8 million electron volt, 8 into 10 to the power 6 electron volt. That is 8 into 10 to the power 6 into 1.6 into 10 to the power minus 19 joules, and substitute in this expression, and you know the values 1 over 4 pi epsilon 0 and 9 into 10 to the power 9, and substituting the value of small z. Small z is for the alpha particles, so for alpha particles the charge is 2, and capital Z is the atomic number of volt, which is 79. And substituting E squared and 4 pi epsilon 0 and the kinetic energy in joules, you will get the same result, and the result is 28 femtometer. That is 28 into 10 to the power minus 15 meters, or 2.8 into 10 to the power 14 meters. So the distance is 2.8 into 10 raised to minus 14 meters. That is a very small value. And so 28 femtometers is very small, which is less than the atomic radius. Atomic radius namakariam angstrom order 10 to the power minus 10 meters order. So compared to atomic radius, this is very small. But this quantity is larger than the nuclear radius. So in the case of gold, nuclear radius is about 7 femtometers. So D is much greater than the nuclear radius of the gold. D is less than the atomic radius, but it's greater than the nuclear radius. So nuclear radius is very small, and D is like that inside the atomic radius but outside the nucleus. So we can say that the projectile is always outside the nuclear charge distribution, and the Rutherford scattering law was derived assuming that the projectile remain outside the nucleus. Scattering formula derive ചെയ്തപ്പോൾ ഇതിന്റെ entire nuclear charge എടുത്തിട്ടുണ്ട്, and we assumed that this projectile is completely outside the nuclear charge distribution. So we can say that the Rutherford scattering formula correctly describes the scattering. So now if we increase the kinetic energy of the projectile, or we decrease the electrostatic repulsion between the nucleus and the projectile using a target nucleus with low Z. So when Z decreases, the repulsive force also decreases, or the kinetic energy is increased, we can have the distance of closest approach less than the nuclear radius. അപ്പോൾ അങ്ങനെയുള്ള എക്സ്പെരിമെന്റ്സ് ഹയർ കൈനറ്റിക് എനർജിയിലും അതുപോലെ Z കുറച്ചിട്ട് ലോവർ Z ഉള്ള മെറ്റീരിയൽസിലൊക്കെ ചെയ്യുമ്പോൾ we can have the distance of closest approach less than the nucleus radius. അപ്പോൾ അങ്ങനെയുള്ള കേസിൽ പ്രൊജക്ടൈല് ന്യൂക്ലിയസിന്റെ ഫുൾ ചാർജും എക്സ്പീരിയൻസ് ചെയ്യുന്നില്ല. ഓക്കെ, ഇതിനകത്തായിരിക്കും പ്രൊജക്ടൈൽ വരുന്നത്. ഇറ്റ് വിൽ നോട്ട് എക്സ്പീരിയൻസ് ദി ഫുൾ ചാർജ് ഓഫ് ദി ന്യൂക്ലിയസ്. അപ്പം അങ്ങനെയുള്ള കേസസിൽ റദർഫോർഡ് സ്കാറ്ററിംഗ് ലോ വാലിഡ് ആയിരിക്കില്ല. അപ്പം റദർഫോർഡ് സ്കാറ്ററിംഗ് ലോ വാലിഡ് ആവണമെങ്കിൽ കൈനറ്റിക് എനർജി ഒരു ആവറേജ് വാല്യൂ Z ലാർജറും ആയിരിക്കണം. അപ്പോഴാണ് ന്യൂക്ലിയസിന് പുറത്ത് പ്രൊജക്ടൈലിന്റെ വരുന്നത്. അതായത് ഡിസ്റ്റൻസ് ഓഫ് ക്ലോസസ്റ്റ് അപ്രോച്ച് എന്ന് പറയുന്നത് ന്യൂക്ലിയർ റേഡിയസിനേക്കാളും കൂടുതലായിട്ട് വരുന്നത്. ഓക്കെ, so if the kinetic energy is an average value and Z is large, we can use the Rutherford scattering formula, and the distance of closest approach is greater than the size of the nucleus. So this distance of closest approach provide an approximate size of the nucleus. അപ്പോൾ ഇങ്ങനെയുള്ള കേസിൽ കൈനറ്റിക് എനർജിയുടെ ആവറേജ് വാല്യൂ അതുപോലെ തന്നെ Z large ആകുമ്പോൾ D is certainly greater than radius, and gives an approximate size of the nucleus. So the distance of closest approach can be used to find out the approximate size of the nucleus. Okay, thank you.